some investigation. Okay? So the setting is we have P an odd prime. So an interesting prime number, not 2, one of the other. P is an odd prime. And we are in the setting, we're in the setting of this thing ZP, the multiplicative group of congruence classes modulo P. Okay? So this we think of as consisting of the numbers, the representatives 1, 2, 3, 4, etc., up to P minus 1. You can think of these as these individual integers, or really they're the congruence classes of these integers. The operation here is multiplication. Now, an element, one of these things, x, we said it's a quadratic residue. What that means is, if and only if there exists a u in ZP, such that x is the square of u. X is equal to u squared. Okay. So you can think of these as we're talking about the squares, but there's this alternative terminology, which is the main quadratic residue. And it's a non-residue if no such u exists. And we did some investigation. I'll put the summary of one of our investigations up in a minute. We looked at modulo 5, 7, and 11, I think. We found in all cases that half of the elements were quadratic residues and half the rows. And that's true again. So we have this theorem that in ZP, multiplicative group, there are, well, there's P minus 1 elements here in total, which is going to be an even number. P minus 1 elements here in total, half of them are residues and half of them are. P minus 1 over 2 residues, quadratic residues, and the other one is P minus 1 over 2 non-residues. And we'll look at the proof of that. Proof is there in the notes. What was the, have you got in your notes there, the results of mod 11? Oh, just reconstruct it. So those are the first 5 elements. If we square these, we should see all of the quadratic residues modulo 11. Okay. There they are squared, or 1, 4, 9. No surprise about those ones because those are square integers anyway, so you know they're going to be quadratic residues. 4 squared is 16, which is 5, and 5 squared is 25, which is 3. 3 modulo. No point in looking further quadratic residues, squaring the higher numbers, because they are just the negatives of these ones. When you square them, you're going to get the same squares as the positives. Even, and you're just going to list 1, 4, 9, 5, and 3. So 1, 4, 9, 5, and 3 are the residues, and then the non-residues. Those are the residues. The non-residues then are the elements, which are 2, 6, 7, 8, 10. I think that's all the facts we need. So what we're going to do now is we're going to work through, well, we're going to leave the notes aside for the moment. I'd rather just read it in the notes. I'd rather do a bit of investigation of yourself and discover the next result. Any questions about this at all? About the summary? Okay. So what I want to move towards is a very natural question now. the natural question is, just frame it roughly as, how does this concept of quadratic residues, how does this fit? You'll wonder about what that means. How does this fit with multiplication? Multiplication in ZP. What could we mean by that question? When you introduce a new concept like this, into the setting, we have these elements, we have this operation with them, it's a group. You've introduced this new idea, so does this new idea fit well with multiplication? Can we discover the link between quadratic residues and multiplication? There ought to be a link because the idea of a quadratic residue is tied up with the operation of multiplication. There exists something whose square is that element. Now, what do you notice? We start multiplying numbers down here. Look at this example, modulo 11. If we start just picking elements and multiplying, what do you see? Well, 9 times 5 is 45, which is 1. 4 times 3 is 12, which again is 1. And 5 times 3 is 15, which is 4. 2 times 4 is 4. 4 times 9 is 36, which is 3. Anyone I haven't done? 3 times 9 is 27, which is 5. So what have you noticed so far? You never had to step over here. You take the product of any two residues, you always find another residue. You take the product of a residue, well, so that's one thing we notice. What about when you take a product of a residue with a non-residue? Do you? Yeah, we checked for you. 5 times 6 is 30. 30 is 8. Modulo 11, so there's 8. 8 times 3 is 24, which is 2. 3 times 10 is 30, which is 8. 4 times 7 is 28, which is 6. The product of a residue with a non-residue is a non-residue. So major kudos to the first person to guess right. What happens if I multiply two of these? Sorry? What does this, so if you multiply two non-residues, you always get a residue. 7 times 8 is 56, which is 1. 2 times 7 is 14, which is 3. Multiply two non-residues. What does that remind you of? Daniel said positive and negative numbers, right? Exact same behavior. When you multiply two positive numbers, you get a positive. You multiply a positive and a negative number, you get a negative. You multiply two negatives, you get a negative. And remember, in real numbers, being positive or negative is what affects whether you have a square root. All of the positive numbers have square roots, real square roots. The negative numbers don't. So in this modular arithmetic setting, we're dealing with the idea of having a square root. And we've seen that the residues, the ones that do, and the non-residues, the ones that don't, their behavior in multiplication is mirroring that we find with positive and negative. Okay, but that's all very well, but we only know that now for 11. What we want, this is mathematics, university level mathematics, we want to prove this for any problem. So we'll give ourselves a conjecture or a theorem. Oh, let's say it's a theorem. I got it's the next theorem in the book, I think, but we're going to prove it in a slightly more hands-on way. So let's formulate the result we want to prove. So we're going to let P be an odd prime. So you may as well close the book. I think everything is on the board, and the proof of the result in the book, we're going to prove it in a different way, so it might miss out. And it uses a piece of notation which we have to introduce to it. So let P be an odd prime. Let's name the two sets. So let R in ZP be the set of residues, we say, and let N in ZP be the set of non-residues. There's three statements we want to prove. Isn't that? What's the first one? Yeah, we proved that yesterday. So we want to generalize this. Yeah. So we want to say if X and Y are both in R, so the residues, we want that to imply that X times Y is in R. The other one was when we took a residue and a non-residue. So we want X in R and Y in N to imply that the product of X times Y is in N. And lastly, the third observation was whenever you multiply two of these, you always get another one of those. So if you have X and Y both being in the non-residues, we want that to imply that X times Y is in the residues. We saw it, we observed it, modulo 11, and we now like to prove it, modulo n. And being in R or being in N is governed by this definition. You're in R if there exists a U such that U squared is equal to U. So X is in R if and only if there exists a U. X is in N if and only if there don't exist a U. You've got a clear definition. So let's try and prove this. Oh well. Somebody got a pen. I've come up without a biro. Somebody got a biro that could loan me? Thank you very much. All right, I'll just let's take a few minutes. Why don't you think about it? Work with each other. Try and puzzle it out. Try and prove these three statements. And the thing we can have recourse to is the definition. Now, when I was doing this out beforehand, when I was planning this lecture, 1 and 2 fall out pretty nicely. 3 is a little bit more tricky. 3, the problem is 3 is you kind of have nothing to start with. Because if X and Y are non-residues, that just means there doesn't exist. And the point we're trying to make up to now, it's hard to get going with an argument when you don't have any ingredients. So if you have the non-existence of something, it's harder to deal with than if you have the existence of something. Then you've got something to work with. So the third one is a little bit trickier, but there is information on the board, I think, which we can look at. Think about how you're going to formulate the proof of these statements. You want to work completely generally, you just want to be working modulo some upfront without specifying what the prime is. And with justification from the definition, maybe that other factor 1 there should be able to reach principles. Think about it, how you're going to formulate it. See what the neighbors think, and try and get a polished version of the report. If you've got any questions, you can ask. I don't think people do, but you could have used the notation and the terminology. You could call these the positive confidence classes and these ones the negative ones. They kind of act like that, but nobody really does. They just call them the residues. But it's a helpful analogy to draw two places. Last volunteers, and then nothing. Also remember, in this group, everything has an inverse. Everything has a multiplicative inverse. You could add on something here, which might be if x is a residue, is x inverse. What's that going to be? I think a positive negative number is the multiplicative inverse of a positive number. Is that positive or negative? Positive. So by rights, this should be a residue. If x is in n, its multiplicative inverse should be now. It'd be nice if we could prove that as well. We're just saying it by analogy positive and negative numbers, but one's a residue, yeah. Yeah, because if they weren't, and we proved number 2, then that would show that 1 was in. Yeah. Yep, so that's a proof of it. Using 2, prove that. And that works for the non-residue as well, because if this x inverse happens to be in R, then the x times x inverse, because of this one, has to be an n, but that would imply that 1 is in observation 1 in 8, and then it's 1 is certainly residue. Okay. Did people catch that? So this follows from property 2 and the fact that 1 is always in R. 1 is always. still be proved. But more time, then anybody else just put up in the market? Remember how I pushed, how I narrated us through similar problems in the past. I mean, if you're trying to prove one, you're trying to prove this implication. Trying to prove this implies this, so you should just assume this. Yeah. So we assume x and y are in R. Now, what does that mean? Unravel that definition. What does that mean? What does it mean to be in R? Yeah. So what it means is it points to the existence of two elements of ZP. And one of them is called U. What we call the other one? V, obviously. Anything else would be incorrect. Is these two other elements in ZP, and the property they have is that x is u squared. So I'm writing equals, but equals, this means under the operation multiplication modulo p, and y is v squared. That's what I mean. So we're proving this implication. So you make the assumption of the condition, you just unravel it by using what the definition is. Now we want to prove the conclusion. So why is x times y a residue? So yeah, so x times y does have a square root, and its square root it has is called u times v. Yeah, because u squared v squared is, as you said, u times v, all of it squared. Yeah. So here is the element, which is the square root of x times y. And it's really nicely made out of the product of the square root of x and the square root of y. So the definition of being in R is that there exists this element such that in the square root of x. Well, here is that element. We've demonstrated that it exists, based of course on the existence of u and v, but it's okay. We're doing this implication. We make this assumption and we draw the conclusion. I.e., x times y is in R. So, okay, yeah, everybody satisfied that that's a proof of one? Okay. And two is a bit more creative for two. See what I mean? It's a lot easier to get going when you're given the existence of something. Given the existence of something, you can do something with it. With two, we've got a non-existent condition. Assume x is in R and y is in N, i.e. there exists a u in R in ZP such that x is u squared, and there doesn't exist a v. Don't go slipping v in the equation. Well, listen to v to that. So,
trying to draw the conclusion that xy is in N.
How do you show x, y is in N?
So you want to consider x times y. U squared times y.
Well, we can't take a square out of y, but why does that mean we can't take a square out of u squared? I get what you're saying. You're saying if you try and square root this, yeah, okay, you can square root u, but you can't square root y. But who's to say you can't square root u squared times y? Right? But you indeed, you and you could be equal to y. Is there anything stopping you being the same as y here? See, when we say x is a residue, it's the square of u, but we're not making any claim about where u is. I don't know if u is a residue or not. No, u squared is not. Well, that's what we're trying to prove. Yeah, so I can't say this is the square of something. But why? We want to.
Let's be careful about just not, proving the result by claiming the result. What's the focus on the conclusion we're trying to get to? We're trying to get to x times y is in N. Now, it's difficult to show that something is in N because you have to show the non-existence of something. But there's a way to indirectly show that something is in N, suggested by the diagram. How do you show that something is in N is not? Sorry, how do you show that something is in N? It's not in R. What proof technique does that suggest? Proof by contradictions. We want to prove it's not in R. So that's the beauty of proof by contradiction, is because that's the strangeness of it, is you're trying to prove that something isn't true, so the first thing you do is you assume it's true. It's a weird idea in some ways. So, and it's a way that you can get going. You make an assumption, it gives you some ingredients, you can do something with them. So we'll assume for the purposes of proof by contradiction, so we're assuming something which we expect to be false. We'll assume that x times y, that it is indeed a residue. What does that tell you? X times y. Sorry?
X times y is a residue.
What does
Being a residue means there exists this other element, which then you square it and get x times y. Now we better not call this element u because u is already being used up.
So, i.e., we're assuming there exists a W in ZP such that x times y is the square of W. So x times y does have a square root. Now, we're in the middle of a proof by contradiction there. We want to show the contradiction. What's the contradiction? Where's the contradiction? The contradiction is going to come from a little bit of algebra, using what we created. We've made this wrong assumption, which has created something, which created this W. We want to show that the W is using this, we're going to show that that's nonsense. So why is it nonsense to say that? Yes. Which means a contradiction is something that's already stated. Yeah. If you're stuck, just start writing anyway. That's the trick. What sensible thing could I write down here? Give me something I can write. Excellent. Daniel is on fire. You put the two together. You put what we had together with the assumption we just made. So where can we go from that? U squared y. Well, one doesn't, you mean you want to apply it over? How do you know that? You wanted to replace W. You can always replace W with the product. Remember, you're in a group. In ZP, where you both sides you get x plus root of y equals x y. Well, can you do that? What's the problem with what you said? You named something that doesn't exist. You named the square root of y. The square root of y does not exist. Y is a non-resident, so you shouldn't refer to it. Yeah, it isn't there. But that points up. Maybe that's what we're going to contradict. How'd you get y on its own? Sorry? What? If you did, how do you get y on its own? You're in a group, you're in this system, ZP, the multiplication modulo P. Well, we don't normally say divide, we're dealing with these modular arithmetic. Yeah. Use the inverse of U, which is around. So very specifically, What's on the right hand side? What's on the right hand side? W squared times don't say x because x is already in something. X inverse, okay, but yeah, times x inverse, or more pertinent to this, not u, u to the minus 2, yeah, 2,
U inverse U inverse. You have to multiply that by U inverse twice to cancel out two U's. Yeah. What is that? What are we looking at there? Yeah, it is Y. Yeah, that's true. Well, what? How do you reorganize that? Re-express that in a pertinent way, in a very relevant way, in a way that's going to and be. We're in the middle of a proof by contradictions. We want to hammer out the contradictions. What is it about Y that's going to be contradictory?
where is y in this picture? Y is in n, that's where we start. So what is this equation telling me?
Seems to say it's an R.
Because it's the square of something. It's this number w times u inverse, whatever that is, all squared, isn't it?
Square W times U inverse, and you're going to get. So that seems to say Y is a square, which is nonsense because Y is not a square. You start off the argument by saying Y is not a square. Right? Now in mathematics, you can't, it's a big trouble if there's ever a contradiction anywhere because it means utter chaos. Everything then is true and false. Existence explodes. So this can't be. So what led us to this? What led us to this? It was the assumption we made for the purposes of contradiction. This assumption. So that assumption cannot be. Cannot be that x, y is in.
So if it can't be in R, it has to be in the on the other place, which is N. Remember, everything in ZP is in R or N. Nothing is in both. So you either are residue or you're not.
This is a contradiction.
This says that Y is in R, which contradicts the fact that Y is not in R.
So the statement that led to that contradiction is times y is in R.
So we conclude x times y is not in R, i.e. x times y is in N. So that's the proof of it there.
You assume x is in R, y is in N, you reach the conclusion x times y is in N. That's With a little bit of algebra, we made an extra assumption and showed that that assumption was a contradiction, or that assumption was true. So that's good. So now we've proved two, so now we know this result about the inverses as well. If x is a residue, so is its inverse. If x is a non-residue, so is its inverse. Now we got the one about 3 to do. So 3, we say x times y, x and y are both non-residues. We want to prove that x times y is a residue. But now, I've struggled with this a bit to try and prove it in the same spirit or on the same level, using the same techniques as we just used for 1 and 2. And I can't seem to do it. But I can do it using something else. So this is the equivalent of proving that if you have two negative numbers multiplied together, you get a positive. That's the analogy. Because we can't use that, you know, we're not in the real numbers, we're in the multiplicative group of integers. So we can't use that. And there isn't a notion of positive and negative. The idea of positive and negative real numbers does not apply. We have this thing which looks like it, residues and one. It's a different thing, so we can't just say it's absolutely true. And of course, the difficulty about proving it like we proved it here is because the assumption you make at the beginning is well, there isn't one of these and there isn't one of these. So that's not much to go on. It doesn't give you anything to use. Non-existence is necessary. You could try doing it as a proof you could try proving the contrapositive. Remember, if you're proving an implication, the contrapositive, this is equivalent to, contrapositive would be x times y is not in R, i.e. x times y is in N. That should imply, well, this is an and statement, whereas when you take its negation, it's going to be an R statement. X is in R or Y is in R. That's difficult to get started with for the same reasons, because when you make this assumption, X times Y is in N, it's X times Y is in N, so what? It doesn't give you anything extra to work with. It's the non-existence. So I think we've kind of used up the easy algebraic arguments in proving 1 and 2, and they don't seem to be enough to prove this 3. Now the idea is going to come from this one. It's a counting argument. Okay. So it seems another idea is needed. So we'll try a counting argument. Using theorem 1. Okay? Half of these numbers are residues, half of them are non-residues. Counting arguments are very, very powerful. The whole subject of mathematics is called combinatorics, which is more or less the mathematics of counting arguments in a way. Consider a non-residue X. Right?
And then we'll consider all the products x times y for y from the group. So I know this says y is a non-residue, but I'm not fixing that yet. I'm just considering y being the general element. But if we consider x as a particular non-residue, consider all these products. We know something about half of them. We've just proved property 2. It says we take a residue and a non-residue, you get a non-residue. So if x is a non-residue, whenever y is a residue, we know that this thing, x times y, is a non-residue. From 2, if y is a residue, that implies x times y is a non-residue. How many non-residues are accounted for in products in cases like this? How many residues are there? P minus 1 over 2. Yeah? P minus 1 over 2 residues. So we're forming P minus 1 over 2 products, which are the non-residues. This accounts for P minus 1 over 2 non-residues. Sorry, I'm slightly running out of time here. I.e., if y1 up to y P minus 1 over 2 are the residues, in each of these, xy1, xy2, xy P minus 1 over 2 are all non-residues, are all in M. Are they all different? Are each of these numbers all different? Well, yeah, because we're in a group. These are products, so x is always the same. If it was the case that 2 of these were the same element, it would have to be that the second factor, y, is the same. But, you know, these are distinct elements here. These are the P minus 1 over 2 residues, so these are all the same. So what happens then when we take a non-residue, U, say, and consider x times U, where can x times U live? Where can x times U live? Is there any space for x times U in here? Well, no, because we've already listed an occupant for each of the spots in here. Because we know from theorem 1 that there's P minus 1 over 2 spaces in here. But there we've just written down P minus 1 over 2 distinct elements, each of these products x times y, and they're all in the non-residues. So there's no space left in the set N of non-residues for this number. This number can't be any of these things, because you could just cancel the x's and it would say U was one of the y's. But U can't be one of the y's because U is a non-residue. The y's are all residues. So you could say, since we have accounted for all the elements, accounted for all the non-residues, XU must be a residue. I.e., x times U must be an R. So that seems to be proof. You can take a non-residue x and a non-residue u. The product x times u has to be a bar. Okay. And it's a counting argument based on counting all the elements and using this theorem one. Okay. It's a nice example of a counting argument. And using this result we already know about how many of these types of elements there are. Constructing all of one kind of them in a certain way, so that any other construction you do must be one of the other. Okay, that's good. We'll continue with all this stuff next week, and I'll see you in the tutorials next week. We'll do some more examples. Sorry.